All right. Hi, good morning, everyone, or afternoon, wherever you are. We're going to wait a couple minutes and let people log in. Okay. Hello to everyone that is joining us. Welcome to Ask Mayfield Anything. This is our monthly live Q&A session on technical topics. We've done a number of them already, so if you're curious to see what other topics we've covered, visit our website, and also for future ones that are coming up, we'll post them there. We record all of these sessions and post them on our YouTube channel. Again, you can access it from our website. Just some housekeeping things. I'm sure everyone is very familiar with Zoom at this point. Just a reminder, if you have questions, we absolutely want to hear your questions. That's the whole point of this session. Use the Q&A button at the bottom of your screen. There's a Q&A feature. If you have questions in there, that's what we're going to be looking at later on, and we'll try to answer them as best as we can. Avoid using the chat feature to put that stuff in there, because then your questions are going to get lost and I might lose track of whether or not we already answered them. We will be putting some links as we're talking in the chat section. So if we mention a particular blog or anything like that, or some sort of resource, we'll put the link in the chat box. And with that, we're gonna get started. So my name is Jennifer Alfson. I will be your moderator today, and I'm the Director of Business Development at Mayfield Renewables. Joining me as our host is Ryan Mayfield, our founder and CEO and fearless leader, and he has been working in renewable energy since 1999 and founded Mayfield Renewables back in 2007. His career has blended technical expertise with an affinity for writing and education. You might recognize him as the trainer who teaches the all-day NEC session at the NABCEP Continuing Education Conference. That is definitely one of our favorite conferences every year. So welcome, Ryan, and yes. I'm excited to do this again.
Yeah, exactly. Thanks everybody for joining. This is great. I'm excited to do this.
Yeah. And joining us today, our guest is Justine Sanchez, and she is our guest speaker and I guess a co-host. She is our solar and storage program director and expert with Mayfield Renewables. Justine's worked in the solar industry for the past 26 years and brings a wealth of experience in technical writing, PV education, and industry leadership to the Mayfield team. Justine's career in solar PV has taken her from a hands-on technician at the National Renewable Energy Lab to developing educational curriculum and teaching hundreds of courses at Solar Energy International, SEI, to acting as the senior PV technical editor for Home Power Magazine. So we are very excited to have you on again. Thanks for joining us, Justine.
Yeah, this is great. Anything solar plus storage, I am excited to talk about. So I'm glad to have you here.
Wonderful. So let's, before we dive into this particular topic, I did want to point out one of the reasons we were excited to talk about this topic is because it is so pertinent to the industry right now, and we've seen a huge need for better training and educational materials around solar and storage, which prompted us to launch these training workshops. So they are led by Justine and Ryan. We have a series of workshops over the course of an entire year. So they're 2 private team workshops per quarter. Each workshop will be a 60-minute presentation followed by a 30-minute Q&A. So these are very intimate opportunities to be able to get one-on-one time with industry experts and get your questions answered and really learn. So there's rotating subjects, including the NEC, NFPA 855, ESS products, design best practices, interconnection, wire sizing, and a lot more. Every workshop also counts towards NAPSEP credits, and you can find a link in the chat section with more details about that, and it's also posted on our website. So definitely reach out to us if you're interested in that. And with that, let's dive into the topic for today. So we are going to be talking about AC versus DC coupling energy storage systems. And I know that there's not a very clear definition of what components make up an ESS system, as in terms of what's defined in codes and standards, but just on a high level, Justine, could you give us what are some of the components that are usually included in an energy storage system?
Yeah, so there actually is a definition. We just don't like its lack of clarity. And so in the 2020, you can go to the NEC and look up, you have to go to Article 706, 706.2, I believe, for definitions. And it'll list out an energy storage system is one or more components assembled together capable of storing energy and providing electrical energy into the premises wiring system or an electrical power production and distribution network. Informational note, an ESS can include, but is not limited to batteries, capacitors, and kinetic energy devices like flywheels and compressed air, which we're not going to talk about today. Energy storage systems can include inverters or converters to change voltage levels or make a change between AC or DC systems. So that's how it's defined. If we actually go to a little diagram, I'll punch ahead here. And, you know, folks that are here, you're probably pretty aware of an energy storage system is going to be a bank of batteries, whether they're lithium or lead acid or NiCads, doesn't really matter. They're storing energy. And maybe the whole energy storage system can include a disconnect and a multi-mode inverter to convert the DC to AC, or maybe it does not. Maybe it's listed together just as an energy storage system with a battery management system. All those details are yet to be worked out manufacturer to manufacturer and in the industry as a whole. But when we talk about in this talk an energy storage system, we're really talking about the batteries, the energy storage disconnect, and a multi-mode inverter. We're gonna kind of package it together for this discussion. And so that's on a high level what an energy storage system is. It's a way to store power for use when you want to use it. So there's that.
Yeah. Yeah, and I know just for anyone who's wondering, like, okay, there's a vague definition. Obviously, that's not helpful. We need a more clear definition and what's being done about it. I know that there is currently a SEAC group, so Sustainable Energy Action Committee has some working groups that they basically get together industry stakeholders and people from the authorities having jurisdiction, building departments, fire departments, and work on submitting proposals to clarify language. And I know this is a topic that actually has been coming up for clarifying the language in UL 9540. So if you're interested in that, I highly recommend you check out SEAC, and maybe Lucas, if you could find a link to that website and put it in the chat. Keep an eye on the work that they're doing because that really helps clarify some of these things. So thanks for that overview, Justine, and let's get into an AC coupled system. So what does it mean to have an AC coupled system? Can you walk us through the diagram of where basically the PV and ESS are, or I guess before we get into that, starting with a, sorry, I forgot we added this slide. Starting with the basic, a non-ESS system, just a basic PV system. What are the components? And let's start there.
Yeah, and the reason I added this slide is because it makes the next one a bit more simple or easier to understand. But everyone that's on this call is probably going to be very familiar with an interactive system. It's the majority of the systems that are out there right now. We're going to have a PV array that produces electricity when the sun's shining, but PV produces DC, and we need a way to convert it, to invert it to AC. And so we're going to have an inverter which does that, changes the DC to AC. And an simple interactive system that you're going to see all over the place is we're essentially just feeding this solar power back through commonly a main service panel through a backfed breaker, and we're offsetting the electricity that we use. However, when the utility goes down, we don't have access to this PV power anymore because these interactive inverters are built to shut down for the safety of the line workers that are going to be dealing with the cause of the outage. Okay, so this little device right here, the interactive inverter, when the grid goes down, it shuts down. It's listed, it's designed to do so for safety. However, as these needs for resiliency increase, there's outages all over the place, either due to wildfires or storms or what have you. People are getting upset. They're like, I bought this whole PV system and it's sitting up there on my roof during an outage doing nothing for me. I don't have any access to the electricity. And so now our industry is seeing a big uptick in demand for backup power. That's one reason to add an energy storage system. And one of the ways to do it fairly simply is to do it with an AC coupled system. And that's basically taking the same gear. You don't have to rewire this PV array or change out your inverter and do a redesign on your PV side if you go with an AC coupled system. But you got to add a lot of other stuff, right? Because now in order to have access to that PV power when the grid goes down, we need a way to first of all store the power for use at night, for example, or when it's cloudy. And so we have to add some way of storing on site that PV power. The other need we have is to keep this inverter alive and active when the grid goes down. As you recall, they're designed to shut down when the utility goes down. And so we have to actually, while we can keep this inverter in place, its output has to get rewired to essentially a backed up loads panel. And so instead of going direct to the main service panel. And the reason for that is we're going to use now, so if we look at this side in our energy storage system, we have our energy storage, our batteries. We're going to have an energy storage disconnect of some sort, whether it's internal or external, depends on the equipment we are using. And we're going to have a multi-mode inverter. And this inverter can operate either grid interactively with the grid or standalone. And standalone means when the grid goes down, it can send a signal over to this backed up loads panel and basically keep the interactive inverter online and keep it producing power so that these loads, so these little lines in here, these are representing circuits in your home that you've decided, I want to have my refrigerator operational, maybe my garage door opener operational, whatever it is. When we've done our design to add this storage system, we're going to think about what do I want to keep operating when the grid is down? And those are the loads that are going to get moved from your main service panel over to a backed up loads panel. And now you have a pathway. First of all, you have a signal to keep this interactive inverter alive and operating and producing PV power, converting PV power to feed these these backed up loads. And you also at night have access to your battery bank. So let's say, it's a storm and it's nighttime. Well, these batteries can provide the power to these backed up loads at nighttime when there's no utility. The other thing that happens is that this multi-mode inverter, because it's also built to the same standards as an interactive inverter, and it has to disconnect from the main service or from your utility, I'm just going to say, if there's an outage, so that it also doesn't send power onto the utility lines, which could potentially hurt somebody trying to fix the problem of the outage. So this line is basically open, and it's open. There's a device inside this multi-mode inverter. We can call it a microgrid interconnect device, I guess is a new term that the NEC put in, maybe it was 2017. And so that little device is in charge of making sure that it's not pushing any either PV or energy storage power back onto the utility lines during an outage situation. So that is basically the outline of an AC coupled system. We're going to go through very specific advantages and disadvantages of this type of design, but we're going to do it, I think, after we describe a DC coupled system so that we can compare and contrast a little bit more clearly once you've seen both architectures. Ryan, do you have anything you want to add that I missed?
I think the only thing I might add to this is as we're seeing more and more new systems come online, or like you said, people with existing systems, existing PV systems adding storage in, a very common refrain is, I want to back up a lot more than what would just be in a, backup load panel. I want to back up my whole house, I think is probably something that installers get that question or that comment a lot. And so there are ways of accommodating that. The big problem, and this is now we're getting the topic would quickly move over to design and of the system, but so there are ways of connecting so you don't have to pull loads out of your main panel. You can back up the whole house, but then that does take into account you have to have specific equipment between your storage system and the main panel at that point. So I just wanted to.
It's a really good point, because what you're limited to is the capacity of your inverters. Okay, so a lot of homes are used to like having just unlimited, 200 amps, let's say, of available power at any time. Well, when you go into that backup mode, into the off-grid mode, the islanding mode, they call it in parts of the code, you're limited to what your inverters can pass.
Right.
And so you may have a bunch of loads that you were like, yeah, let's just back up the whole house. Well, you can't if you don't have the inverter capacity available to you. And so that's, if we're going to bring up a whole home system, that's one key thing to think about as you design systems. I guess
I was just wanting to point that out, because we've done not necessarily a super simple diagram by any means, but it is one way to do it. There are multiple ways of incorporating that. And so just wanted to make sure everybody is.
Oh, that's key. That's a question we get every day. Like, just
exactly.
back up the whole thing.
Right.
And just a reminder to everyone on participating to please put your questions in the Q&A section. We're getting some that are coming in the chat. And then I saw some folks that are raising their hands. We're not going to call on you, sorry. So if you have questions, type them into the Q&A and we're going to go through them. So one just came in right now as you're speaking, Justine, that I think you can answer. From Christopher Ho, thank you for participating and thanks for submitting your question. He's asking, will the string inverter recognize the frequency shift from the multi-mode inverter through the backup loads panel when the grid shuts down?
We're going to talk about that a little bit more, but yeah, I'd like to wait to get to the charge control side until we discuss these a little bit more, but it's something that it would be good to check. You want to make sure the multi-mode inverter charge control mechanism for when the grid is down, and it wants to make sure the energy storage, or we want to make sure the energy storage doesn't get overcharged when the grid's down and you're not using much power, because you've got this big array and potentially a lot of energy coming from the array passing through the inverter, and we need a way to shut down those inverters if the batteries are full. And so that's what the frequency shift will do. However, I wouldn't always assume that that's the case. I would probably do a little digging. I'd call inverter manufacturers and make sure that they're okay with the charge control scheme between these inverters, and that frequency shift method is going to work for them. So, but I'm going to stop there. Okay.
Right. And just to high level recap, basically an AC coupled multi-mode system means the energy coming out of the PV system is first converted to AC before it's then connected to an energy storage system. So that's why it means AC coupled. So you think AC, that's where they come together. Justine's going to talk about the difference with a DC coupled. So Matthew Pius, to answer your question, thanks for being on here. So he's asking, can an AC coupled multi-mode system use only the multi-mode inverter, or do you also need a separate interactive inverter?
Oh, an AC coupled system with only a multi-mode inverter?
So basically that would, so to answer, no,
Yeah.
it's gonna have two inverters. So AC coupled, meaning the PV inverter or the interactive inverter is gonna convert the energy coming from the solar system first, and then you're gonna attach it to an energy storage system. So that's why there's two inverters required there. Justine's gonna get into what a DC coupled system looks like, and I think that might clarify, you know, when and only one inverter is needed.
Yeah, and we're keeping this discussion to just solar. So yes, because our solar array produces DC, we have to have a way to change it into AC. And thank you, Jennifer, for reminding me why this is called AC coupled. They're connected on the AC side. So which leads us into, I'm going to actually come run to this one, then we'll go back to the pros and cons. So this is our DC coupled system. So let's say we are going to start fresh. We don't have a retrofit. We're actually starting from scratch, and we're going to design a system. And in which case it would be a lot easier to consider a DC coupled system because none of this gear is already in place. We don't already have an existing PV array with an interactive inverter that's already installed on the roof and designed and ready to go. We can actually step back for a minute and be like, whoa, if I have options here, what could I do? And why would I maybe want to do it this way? So let's talk about a DC coupled system and what that means. To Jennifer's point, we are combining on the DC side of the system. We have a DC source, a PV array, and another DC source, an energy storage system. They both are producing DC electricity. So there's no need to convert from DC to AC at this point, because we can charge our energy storage system directly from another DC source, which is the PV array. And what's not shown here is a charge controller. But we can assume there's going to be a charge controller in this circuit so that when the PV array is producing electricity, when the sun's shining, there'll be a PV system disconnect, of course, because we always have disconnects. And there'll be a charge controller. Maybe it's inside this multi-mode inverter package, or maybe it's separate, but know that it's in there. And a charge controller's job is to basically monitor the batteries, and it's accepting power from the PV while the batteries are needing charge. And as the batteries fill up, you have a charge controller that's watching the voltage level of the batteries and the amps coming in and saying, they're getting a little bit full. Let's taper off the PV. Let's turn that down a little bit because we don't want to overcharge these batteries. That would be bad for the batteries, bad for us. And so that charge control is happening on this DC side. We can charge from the PV array to the energy storage, and that's its own, almost like it's a DC bus essentially with its own gear that's all designed to work together at the right voltages and with no DC to AC conversion loss, okay, because it's straight DC to DC on this side of the system. Then, okay, let's say batteries are full, sun is shining, and now we have options here with our multi-mode inverter. We can, if we are producing more energy than we're using within our backed up loads panel, we can send that on to the main AC panel and feed the loads in the main part of the house, or whatever we've decided to keep on the non-backed up load scenario. And if we're using more, or sorry, if we're using less than we're producing, that power can get sent back to the utility for a credit, just like in an interactive normal system. But should the grid drop out, this line opens up again, just like it did last time with its microgrid interconnect device is going to open this line up, and we still have our powered up backed up loads panel that can pull power from the PV or the energy storage system. Depends on the time of day, what the loads are requiring, where that power is actually coming from, but it has its pathway that's opened, and we have this backed up loads panel. So the keys here are that we're combining the PV and the energy storage on the DC side of the system, but we're providing the same functionality that the AC coupled system did, but with some inherent advantages and disadvantages. So I think I can now start talking about the advantages and disadvantages, unless we have any other basic questions.
Yeah, just a couple comments that are coming in. So, and I think you pointed to this or alluded to it, But Ezra put in the comments,
Hi, Ezra.
don't forget, yeah, hey Ezra, don't forget that battery capacity limits loads even more than inverter size. So I think that is an important thing to note, is that, you know, just because you have an energy storage system doesn't mean that you're going to magically be able to power all of your loads and stream your Netflix and blast your heater and
Absolutely.
have a lot of money.
Yeah.
I mean, it's technologically possible. It's just cost prohibitive at this for most people.
I think that's a really good point. We've lost sight as a little bit because we've gotten so plug and play with this equipment. Folks are just like, oh, just give me a power panel. You know, I'll just be able to, like, you know, back up everything. And way back with this, when this industry started, and the majority of the systems were off grid because it was cost effective to create an off grid system for a home that was off, you know, didn't have access to electricity. We went through all these steps in painstaking detail about adding up all the loads in the house. And then once you have your load profile, you size your battery bank, depending on the load of how many amp hours and watt hours you're going to need over the course of the day. And then once we had our battery bank sized up, we'd size our loads. Then we would size our inverters and our PV array and so on. And it was all built up around the loads. What are we using? How much do we have to have? And all those components had to be designed to meet that end goal. With grid-tied systems, we're so used to having an excess of energy that we've kind of lost a little bit of that insights into, or even like homework that we used to always have to do as part of a PV system design for off-grid. And it's a really good point Ezra brings up. If we don't have enough battery capacity, it doesn't matter if we have a bunch of inverter capacity. We have to have inverter capacity and battery capacity to feed whatever load profile we need to feed for as long as we want to feed it. And so it's a much more in-depth calculation than just throwing a power panel, sorry, a power wall on in your garage.
And this kind of ties into another question that came in from Kathy Nicholson. Hi, Kathy, and thanks for submitting your question. She's asking, do you consider the span panel a good solution to the backup loads and the quote whole home backup challenge? I think we kind of touched on this already. The concept of a whole home backup is just not realistic. But I think maybe Justine, you can speak to these new smart panels that are coming out. So there's some smart panels that are supposed to be able to, instead of having basically you swap out the main service panel with a smart panel. And then that way you can identify, okay, these are going to be my backup loads, but say the grid actually does go down, you're using it and you're like, oh shoot, I forgot this, wall outlet or this part something that I really want to have powered. You have the ability to change it real time, which loads, basically which breakers are going to activate. So what are your thoughts on those?
I think it's great. I mean, we're coming up with solutions every day that are dealing with the issues that, these guys are bringing up, as far as like, well, okay, well, what if I have a smart device that can just click off certain loads under certain criteria that we give it, and have a smart loads panel, and problem solved. Yeah, we're going to be throwing more technology at these issues as the months and years roll on. But we still ultimately have to think about the root problem. Like I can't say, yes, you can back up your whole house. You totally can if you have enough batteries and inverters and then add a smart panel, some smart load panels in there as well, and get a kind of a more engineered design. But we just can't assume that with this basic equipment and no thought that we're going to be able to back up somebody's whole home.
Mm-hmm.
So
yeah, it's things you have to put a little more thought into it than just, oh, I have storage, I can power everything.
Exactly.
And another question just came in as to whether or not we're recording this. Yes, we are recording it. We will send out a recap email with the link to the video recording. It will be on our YouTube channel and it will also be on our website. And then someone else asked if we could type in the answers while we're talking, and I would love to be able to do that, but I can only focus on one thing at a time. Like, it's hard enough to juggle these. So hopefully you're paying attention, and we will post these after so you can always recap what our answers were. Okay, so take it away, Justine, in terms of advantages, disadvantages.
Yeah, so let's, we'll kind of click back through the AC coupling. Quick reminder, we've got 2 inverters here, accessing the power. Basically, we're kind of meeting at this backed up loads panel between these 2 different inverters. What are some of the advantages of this particular design? We've already said retrofits. That's going to be the big, in my mind, probably the biggest one. We don't have to do a redesign. We can start adding our energy storage without reworking the whole PV system. The other one, which I mentioned briefly before, is a higher inverter capacity. If you look, we've got 2 inverters. Okay, in the DC coupled one, we have a single multi-mode inverter that's going to be supplying our backed up loads panel. That means in addition to the energy storage capabilities, we are limited by the size of this multi-mode inverter, how many kilowatts we can produce at any one time for our backed up loads. So if we have, you know, a lot of high usage loads, or even, you know, it depends on what you're trying to do with your backed up loads panel, but you might over amp this multi-mode inverter in short order if your loads are large or using a lot of things at the same time. One of the advantages of an AC coupled system is that we've got both these inverters feeding this backed up loads panel. Okay, so now we have the kilowatt hour capacity of this, assuming it's sunny. Okay, we have to, I need to back up. I mean, it does have to be sunny. You do have to be producing power. And, you know, if you're maxing out this inverter with whatever you're producing, then you'll have the full kilowatt rating of that inverter to feed this backed up loads panel. And then down here, if your energy storage system, assuming it's charged up, and this multi-mode inverter is operating and not in a low voltage situation, which we'll discuss in a moment, we also are utilizing that power into this backed up loads panel. So we have more capacity, kilowatt capacity, inverter capacity, assuming that the actual energy sources are supplying that capacity to feed our backed up loads panel. So that's another advantage of an AC coupled system. You have 2 inverters, more capacity for feeding those backed up loads, assuming the sources are supplying that capacity. Redundancy, this is one that I hadn't really thought about much before, but if you think about it, in a DC coupled system, you only have 1 inverter. If this inverter is out for repair for whatever reason, even though the solar panels are producing power, you're not going to be able to utilize or backfeed any electricity from the solar into anywhere. I mean, if that inverter is gone, your pathway to your AC side of your system is gone. And so, which means you're not getting credits for those kilowatts you're producing when the sun's shining and so on. So there is some redundancy when you have an AC coupled system. However, you'd have to have some kind of bypass switch, because remember, if you pull this box out and you're depending on its pathway to route the power back over to your main AC service panel, you'd need a bypass switch to do that with. Okay, so it's not just assumed you have this redundancy. It depends on how you've actually designed and installed the system. Because if this pathway, if it's dependent upon this multi-mode inverter and that thing is out for repair and gone or something, then you don't have that pathway. But if you have a bypass switch, then you could still have your interactive inverter producing power while your multi-mode inverter is at the shop, and you're still getting credit for that electricity. So, or
vice versa, right? If the interactive inverter goes down, you can still use the multi-mode inverter. And
well,
is that
only true? But you don't have access to your PV array.
But if your batteries are already charged up, say, and your interactive inverter goes down.
Yeah.
And if you can charge from the grid, then you would still have that ability.
That's true. Yeah.
Is that allowed? I know that was something that was of large or great debate in terms of whether the utilities were going to allow people to charge from the grid when the rates were low and then sell back. Is that an issue, or are you allowed to charge your batteries from the grid at any
You're
time of the day?
totally allowed to charge your batteries from the grid.
Okay.
If you are getting perhaps an incentive, that's where it gets tricky. And then, right, if you're taking advantage of the time of use metering, you might have some,
Yeah, there may
you
be
don't want to
something
sell
there.
that power back, buy it at a low rate and sell it back to them, back to the utility. But you can charge your batteries from the grid.
Okay. And so before we move on from this slide, and you may have already sort of answered this, but Becca just submitted a question. Hi, Becca. Thanks for joining us. She's asking, in an AC coupled system, can the multi-mode and battery be installed remote from the straight grid tied system? So the grid tied inverter, or what we're calling interactive inverter, if the interactive inverter is in the garage into a sub panel fed by the main in the basement, and then with proper switch gear, putting the multi-mode inverter and battery in the basement, feeding critical. And I want to correct you. You said critical loads, but there is a distinction now. The correct wording is backup loads. And the only reason we say that is because there is a definition for what critical loads means, and that gets into some things. So backup loads, you might want certain outlets that aren't considered critical as your backup load. So just careful with your terminology there. But
so yeah, she brings up a good point. You don't have to co-locate the inverters. And that is one of the advantages, actually. Another advantage maybe we should add to this list is that we could have your interactive inverter remotely located on a different part of the structure. And actually, if you get into big systems, it is common for those inverters to not be co-located very close together. Although then you, like she said, you need switch gear and other componentry to make it all happen. Right. But yes, that is absolutely a way to do it.
Yeah, and depending on the system, I mean, it's the disconnecting means and all those kinds of things, which likely are already going to be there. If your interactive system is in place, all that is likely in place already. So adding a storage system, multi-mode inverter at a different location is not going to be a difficult task, or won't be, it would be allowed, I should say.
Mm-hmm. There are issues when you get into disconnects and co-locating your disconnects. Maybe you have to double up if your right. stuff is far apart, and maybe you have to add another disconnect so that everything is at the main service panel accessible, and so on. We're not going to get into the code requirements in this particular talk, but just it might be another thing. You may have to add a disconnect somewhere if it's not already at a readily accessible location. Okay. Yeah. I'll stop there.
All the more reason to sign up for Justine's workshops later this year, where she is going to dive into all the code requirements.
So then, okay, I'm going to move into the DC coupling primary advantages. Okay, so because we haven't hit on these quite yet. So efficiency. Now, I'm kind of curious. Wait, did I skip something? Oh yeah, the bottom one. Okay, thank you. Because I hit this from both sides. Either one could actually be more efficient, depending on when you're utilizing the electricity. So in the AC coupled situation, here's our AC coupled situation. Our interactive inverters are commonly more efficient than our multi-mode inverters. So if you're utilizing the power as it's being produced, and you're not running it back through this multi-mode inverter to charge batteries and then back through, say at night, and you're using it during the daytime, you get to take advantage of this higher efficiency inverter, essentially. Let's say you're, for whatever reason, your majority of your loads is during the day. Maybe it's a school, and they're using that power as it's being produced with the students in session. Well, then maybe it could operate more efficiently. So that could be an advantage of an AC coupled system. Depends on if you're using the power when it's being produced. However, because, well, let's go ahead and stay on this diagram. A DC coupled system could be more efficient in the sense that we only have one inverter in a DC coupled system rather than 2 like we have here in the AC coupled system. So if we are having to run our PV array through our interactive inverter, there's an efficiency loss there. And then let's say we're utilizing that PV power to charge batteries. We have to change it from AC back to DC to get into the batteries, and then out of the batteries, but from DC back to AC to our backed up loads panel, say at night. Okay, and then you have efficiency losses here and here with an AC coupled system if you're utilizing that power at night. So if I jump to my DC coupled advantages, I have efficiency as one of the advantages to a DC coupled system. And that's with the assumption that if you're basically having to convert the DC to AC, AC to DC, and DC to AC again.
So more efficient when you're using it to charge the batteries directly.
Exactly.
When you're considering that portion of the use. Mm-hmm. Right.
Yeah. So the big one that I really want to get to today is the full PV array power. Okay, so I'm going to go all the way back to our initial diagram here, our interactive system. And those installers, designers that are on the call, they're very familiar with the idea that your PV array might be much bigger in capacity, in DC capacity, than your interactive inverter can process. It's called a higher DC to AC ratio. And so designers have been doing this for years. They realize that when the sun's shining and it's daytime, it's a bit warmer, maybe we don't have perfect conditions to produce the entire capacity that this array is actually able to produce. And so they downsize the inverter because in a lot of cases, they're not going to be able to utilize that extra kilowatt capacity of the array that it can produce under laboratory conditions. Okay. And so it's very common to see, let's keep this in the residential setting for now, but let's say we have a 5 kilowatt array, we might put that on a 4 kW inverter. Okay. And so there's a limiting factor here in that. And so if we were to produce 5 kilowatts with the PV array, we can't pass any more than 4 through this interactive inverter. Okay, and so that's called a clipping loss. Let's say it was a bright and sunny day, super low temperatures. We are throttled, basically we have a bottleneck. It's okay, it's not gonna hurt any equipment. We just can't produce any more than this interactive inverter is rated for. But it's a way to kind of, it's a financial calculation you do. Like, okay, it's less expensive to buy a 4 kW inverter than a 5 kW inverter. I mean, not by much anymore, but that's where the thing, when you start getting the big systems, those calculations become more important. And so when you have an AC coupled system, you're limited by that same interactive inverter, okay? So if you have your 5 kW array here and a 4 kW inverter, you're never gonna be able to get more than 4 kW off your array, even if it's producing 5. So, but if you have a DC coupled system and you don't have that limiting piece of equipment between your PV array and your energy storage, you can utilize the full capacity of your array if it's available. And they're starting to design systems, bigger systems with this in mind. Let's talk megawatts. And where you also have limitations on when you get into your interconnection limitations with larger systems and even with smaller systems on how much we're actually allowed to backfeed into the grid and into our bus bars and so on. And so on occasion, we will keep using that higher DC to AC ratio, but let's say in a larger system, we could design a much bigger PV array than we're allowed to actually connect with a multi-mode with any inverter because of limitations at our interconnection. But we could oversize our array a bit and charge the batteries for discharge later, say in the evening. So we could put in, say, I'm going to talk big numbers now. Let's say we put in a 2 megawatt PV array and we have only a 1 megawatt inverter and we have an energy storage of whatever, 1 megawatt, 2 megawatts. Well, during the daytime, we can pass a megawatt through the inverter And we can pass another megawatt down to the energy storage for later use in the evening time when the sun's not producing anything and not what's my word? Be limited by our interconnection. Let's say our interconnection is limited at a megawatt. Okay, so we're time shifting when we can utilize that PV array. But it's a way to build in a bigger PV array, which you couldn't do with an AC coupled system.
Right, and we're seeing these more and more too, and they are, especially for DC coupled large arrays, where you can get these quite large DC to AC ratios. When if you just look at the PV to the inverter ratio, you're crazy to do 2 to 1. But if you're able to incorporate storage and store that, then that's where it becomes a possibility.
Absolutely. Yeah. And there is a great discussion happening right now between Marvin Hammond and Drew Gillette. Hey, you two. And shout out to Marvin, who's going to be one of our guests on the next AMA session. In terms of, can you clarify? So yes, charging batteries from the grid. So yes, you can charge the batteries using electricity coming from the grid, but can you then export it and get paid from your batteries to the grid? So Marvin's saying no, Drew's saying yes. So which is it?
My easy answer would be check with your utility and what your agreements are. As the safe middle of the road answer there.
I like it.
All right. So the debate continues.
All right. Well, I'm going to run into the next one because then we have some questions I think we want to try to get into that were submitted. But the last one I wanted to mention, which actually gets into one of the questions, is resiliency. And that is the idea that, okay, let's say the scenario arises. Let's go back to our AC coupled system where we didn't do a good job of telling our client how much energy they had available to them, and they went ahead and it's an outage, and they kept running everything they wanted to and then some in their backed up loads panel, and they got to the point where this energy storage got so low in voltage that it shut down this multi-mode inverter. Okay, because the inverter has to there's a minimum threshold that it needs to see to operate. And so then if the multi-mode inverter shuts down due to a low voltage situation, now all of a sudden you have the situation where it's down. It's not producing any power, which means it's not feeding this backed up loads panel, and it's not giving a signal to the interactive inverter, which means it shuts down. Okay, and so there's no way for this PV array to step in and charge the batteries, because it has to run through this whole circuitry and be woken up by the interactive inverter, which is now shut down to low battery voltage. And so in contrast, a DC coupled system, because the charging is all on the DC side and doesn't depend on this multi-mode inverter to be up and functioning, in that scenario, you could still have, oh gosh, I don't have any power in my backed up loads panel, but at least your PV array, when the sun, the next day, the sun comes up, you have access to PV array power. This is tied together on the DC bus, and you can get those batteries charged up to turn the multi-mode inverter back on once they're at an acceptable level and start producing power again. You're not dead in the water like you are with the AC coupled system. So that's what we mean by resiliency, in the sense that we have access to that PV power even if the multi-mode inverter shuts down due to a low voltage situation.
Right. And so one quick question that came in, let's see, from William Chen. Thanks for submitting your question. Which one is easier to permit? AC coupled or DC coupled energy storage systems for commercial systems?
Well, I don't know if it's really about permitting as it is about finding the appropriate equipment for the job that you're trying to do. So that's I don't think that there's an answer. Honestly, if you're getting into a commercial system, you're not picking your equipment based on ease of permitting. You're picking it on, is it going to do the job I needed to do with, maybe there's generators on site, maybe there's already existing backup panels that you're going to be dealing with. What equipment can I even get right now in the capacity size that I need? That's a big one. So it's really not about permitting.
Got it. Yeah, more important to figure out what equipment is going to be suitable for your application.
Yeah.
Got it. All right, let's keep going. We only have 10 minutes left, really 5 minutes left, and then we got to wrap up. So should we jump to the questions that were submitted ahead of time? Or are there more points that you want to touch on?
I mean, some of those we've already answered it just throughout our discussion.
Okay. There's one that came in from Ezra. I'm not sure if you saw this one. Does the charge controller make, and I think he asked this while you were looking at a DC coupled system,
Okay.
Does the charge controller make any input voltage changes, i.e. MPPT input range for battery voltage?
Is he asking that as a real question, or is he just wants me to talk about how you can get MPPT charge controllers at a variety of voltages? I'm not exactly sure if it's more of a, hey, Justine, why don't you mention this? Which I'm going to go with that.
Okay.
So,
well, in true politician form, you just take the question and morph it into what you actually want to answer.
yeah, I'm not good at that. Let's see. So one of the, I really wish we had a charge controller on this. I think I'm going to put that as a request in for the next round of diagrams. But it's a very good point. Charge controllers in a DC coupled system. Now, thankfully, we do have options, higher voltage DC options. One of the problems way back when we started doing AC coupled systems, just even DC coupled systems and comparing the two is that we had charge controllers that were limited on the DC input and output, mostly input side, to maybe 150 volts, maybe 200 volts, but now there's some options at 600 basically. So I'm thinking residential in my mind. And so that we can still wire our PV array at a high voltage and have those efficiency gains in wiring, less overcurrent protection when it comes to series fusing and stringing your array and how you're going to configure that. And so now, thankfully, on the DC coupled systems, we still have access to 600 volt charge controllers, so we can still string a highly efficient, high voltage PV array and put in a high voltage charge controller rather than having to be limited to smaller voltages like 200 volts, which means we need a lot more strings to make the same power than we do a longer string at higher voltage. And so, and then we've got to, of course, choose a charge controller that works on the output side to our battery bank at the voltage that we are going to size our battery bank voltage to. So whether that's 400 volts or higher, we would need a charge controller that's going to work within the battery bank voltage as well.
Mm-hmm.
I don't know. Ryan, did you see any
No, and I think just the big answer is we can. There's there's these MPPT controllers, and I think one of the other big things is you referenced back in the day, now we have 60 and 72 cell modules, so essentially you're having to use MPPT controllers to be able to make sure you match your battery voltages. So, but thankfully we have lots of options now for higher voltage charge controllers to match up to our battery banks.
Excellent. And so let's see, last question here. And this is one that came in ahead of time from Ed of GES Solar. Thanks for submitting that. And he's asking kind of a specific question, but maybe you can answer it in a little more general terms. We're working on a proposal for an AC coupled system for a customer with an existing 12 kilowatt system with microinverters. and it's connected to a line side or supply side. Now the owner wants to add an energy storage system. So the questions are, can we convert the entire 12 kilowatt system to be an AC coupled system, or do we need to split it? And then the second question is, what battery inverter or battery combo will work best with this existing microinverter system?
So that's a full design question. Without knowing the specifics of their main load panel, obviously they're doing a supply side connection already, so the PV array is too big to be just be backfeeding. Main service panel, we couldn't really appropriately answer this question without looking at the details of the system beyond that information. And so, but one thing we are seeing is, yeah, sometimes you do have to split up the array to utilize this equipment because of how you're going to interconnect your backed up loads panel and what you want to feed that, and what package you're going to use when it comes to energy storage. So unfortunately, there's no easy answer to that question. That's a full design consultation.
Yeah, and so speaking of which, we do offer design services. So Ed, if you need some support with going through a design like that, reach out to us. We have a really great design team that can help you out. And okay, I said that one was going to be a last question, but I lied. One more. Very last question. So given that all of these energy storage components are usually manufactured by different companies and designers are having to piece together all of this, how can a designer ensure that their design is code compliant?
Well, it takes work. It takes looking at a lot of different code sections and making sure you're complying with all those different code sections. We are working on curriculum right now to deal with that. It's not plug and play. There's a lot of different code sections that you may not be used to working with, whether it's 706, 710, and then if you're integrating generators and things like that, you're going to get into potentially other code sections that you haven't worked with before. So it takes a bit of research and patience and dialogue between manufacturers, between your system owners, between the HJ, and someone who's really dedicated and digging into those code issues to make sure it is all compliant.
Yeah, and so with that, definitely, if you can actually go to the next, I think a couple slides over, Justine. So we are offering again these, go to the next one. Yeah, so these storage workshops that we mentioned throughout this, Justine just spoke to exactly why we're offering this. It's complicated and the industry is changing very rapidly. Some of these codes aren't written in a way that is either even physically possible to obtain the way or to execute them. So you have to learn, and one of the best ways that you can do that is learning together. So reach out to us about additional workshops coming up on energy storage. And then our next AMA session, if you can go back to the previous slide, our next AMA session, we're very excited about having Pure Power Engineering join us. They are one of our partners, and they're going to be talking about free voltage drop and as it relates to clipping. And they have an article on their website right now about this topic. We'll send out some more details about that so you guys can read up on it and submit some questions ahead of time. And with that, thank you everyone for joining us. And we really appreciate all the questions and participation on here. If we didn't get to your question, we'll try to follow up with you after this and answer them. Always feel free to reach out to us. You can email us at technical@mayfield.energy. Justine, if you go to the last slide, I think our contact info is on there. And join us for our next AMA session. That's going to happen end of February. And thanks again. Have a great day.
Thanks, everyone. Thanks, Justine.
Thanks.
Jennifer.
Thank you.